chapter 18, physics, question number 3, 4, 5, 6, 7 and 8. Let's go to question number 3. Mount Everest is approximately 9 kilometers high. Calculate how much less a mountaineer of a mass 100 kilograms, including backpack, would weigh at its summit compared to her weight at sea level. Would this difference be measurable with bathroom scales? Right? So let's see. So 9 kilometers high. So the Earth's radius is given as 6,400 from the center. Then the Mount Everest is going to be 6,409. Right? So that difference is what we need to calculate. Right? Weight at the surface, then weight at the top. That is the difference. Right? So what is the equation that you can use? You can actually simplify this using using your knowledge. The first thing that you need to do is, now delta F is what we need to figure out. Delta F is equal to weight at the surface. Weight at the surface is mg, right? Simple mg. Then weight at the top of Everest. Top of Everest is the other one. To find the top of Everest, you have to use the equation g m upon r squared, right? So the mg you can calculate, because the 100 is the mass that has been given, multiplied by 9.81. So that would give you the value. That is 981. 981 is the answer for weight here. So that is newtons in units. Then G capital M simple m, right? G, the capital M mass of the Earth has been given as, I will leave G as it is. You know the value of that, 6.67 into 10 to the power minus 11. Then mass of the Earth is 6 into 10 to the power 24 multiplied by, and this lady has a mass of 100 kilograms with the backpack. Then that divided by, now the R is not 6.4 but it is 6.409, right? That has to be into 10 to the power 6 kilometers. That has to be squared, right? And when you simplify this, you will get answer to be 7 newtons, right? 7 newtons. The 7 newtons is actually something that can be slightly seen in that on a bathroom scale. So slightly it can be noticeable. However, there would be other factors that would be more significant, like when you climb to the top of the mountain, you will be losing a lot of water, right? So you will be dehydrated, so you would have lost a lot of water. But other than that, this, if that person has had a lot of water, as much as she has lost during the climb, this would be slightly detectable. So that is the answer for question number 3. Let's go to question number 4. Calculate the gravitational field strength close to the surface of the moon, close to the surface of the sun. So they have given the details in table 18.1 here. Close to the surface of the moon and close to the surface of the sun. So let's using the details, let's try to figure out what they give us. I would suggest you look at figure 18.1 in your textbook when we do these questions, right? So gravitational field strength on the moon, we can take, we know the equation G equals G m upon r squared, right? So G is universal, I will leave it as it is. Then the mass of the moon is 7.4 into 10 to the power 22. That is from the table. that has to be divided by r is the radius of the moon, that is 1.74 into 10 to the power 6, that has to be squared. When you simplify this, you will get simple g to be 1.6 newtons per kilogram. Newtons per kilogram. So we will get the answer 1.6 newtons per kilogram. That is the simple g for the moon. Now part 2 is towards the close to the sun, surface of the sun. So they have given sun's mass is 2 into 10 to the power 30 and radius is 700,000 kilometers. So let's use those details to find out the gravitational field strength. Once again, we use the equation G equals capital G m upon r squared. Capital G is again I will leave it as it is. It is 6.67 into 10 to the power minus 11 multiplied by mass is 2 into 10 to the power 30, that is from the table, divided by r squared is 7 into 10 to the power 8, that's squared, and this will give us 270 newtons per kilogram. 270 newtons per kilogram. So you can see that it has very much of a higher value for gravitational field closer to its surface. Right, let's go to question number 4b. Suggest how your answers above help to explain why the moon has only a thin atmosphere while the sun has a dense atmosphere. Because gravitational field strength is quite weak on the moon, so gas molecules can easily escape. However, the sun has a very high field strength and gas molecules are pulled very close to each other. As a result, it has a very high density. The atmosphere has a very high density. Right, question number 5. Calculate the Earth's gravitational field strength at the position of the moon. At the position of the moon. So we can, it is simply using the values that have been given. Distance from the Earth. So the moon is 3.8 into 10 to the power 5 kilometers, 10 to the power 5 kilometers away. Right, so they have given in kilometers. Remember, they have given in kilometers. Right, 3.8 into 10 to the power 5. So how do you convert that into meters? You multiply it by 10 to the power 3. Then it is going to be 3.8 into 10 to the power 8. Right, so that is another calculation. If you make that mistake, if you use kilometers instead of meters, your answer is going to be wrong. Right, so part A, the equation is G equals gm upon r squared. So capital G I will leave as it is, multiplied by m is m is 6 into 10 to the power 24, because that is what causes the field. It is not the moon we are talking about. They are asking what is the gravitational field strength caused by the Earth on the moon at the point where the moon is there, divided by the separation is then 3.8 into 10 to the power 8, and that has to be squared, and you get your answer to be 2.8 into 10 to the power minus 3 newtons per kilogram. Right, newtons per kilogram. Then let's go to part B. Calculate the force the Earth exerts on the moon. Calculate the force the Earth exerts on the moon. So now that is per kilogram. Right, so then hence determine the moon's acceleration towards the Earth. So what happens is the force is equal to mg. So the mass is 7.4 into 10 to the power 22, and G we just calculated 2.8 into 10 to the power minus 3, and the force is going to be 2.1 into 10 to the power 20 newtons, right? Then what is going to be the acceleration, right? We use F equals ma, then A equals F upon m, right? We know what F is. We know what F is, we know what m is, and when you use those values, you will get 2.8 into 10 to the power minus 3 meters per second squared, right? If you are not sure what F and m are, look at the table. So the F is 2.1 into 10 to the power 20 newtons. Mass is from the table, right? Let's go to question number 6. Jupiter's mass is 320 times that of the Earth, and its radius is 11.2 times the Earth's. The Earth's surface gravitational field strength is 9.8 newtons per kilogram. Calculate the gravitational field strength close to the surface of Jupiter. Once again, we have to use the equation G equals gm upon r squared, right? So because the Earth has a, Earth has the gravitational field surface, at the surface 9.81, right? So 9.81 is what we have closer to the surface, right? So then if you put all those values, the number of times that it is going to be, right? So they have given the details. Jupiter's mass is 320 times that of the Earth, and the radius is 11.2 times that of the Earth, right? So you use those values, then you will get 9.81 multiplied by 320 divided by 11.2 squared. This will give you 25 newtons per kilogram. You can recheck your answers by individually applying for the equation as well, by taking the Earth as 1 unit, 1 multiplied by 320 divided by 1 into 11.2. So the same answer will come, 25 newtons per kilogram. So that is question number 6. I hope you understood. If you have any doubts, please raise questions. I will teach them again.